what I will present today goes back to an idea which also was promoted by Keshav together with Catherine Rosenberg, I think in 2013 or something, or 12 or something like that. And it's more or less, the original ideas from the 90s. It more or less tries to bring the analogy between internet and a power grid to a fruitful operation. I don't know whether this will end up in something which is technologically used one day, but as I will show on the next slide, we all will run into a problem, at least from a German point of view, in which there's no solution, and the energy packet grid might be one. You have a large list of authors, and you might ask why, because it's a group, it's 3 professors. So myself from energy informatics, but also Martina Zitterblatt, whom Keshav knows well, for telematics, internet technology, and Mark Hiller, who is our power electronics professor at KIT. So we tried as a union of 3 disciplines to think about this idea. Why do we need line management in the energy packet grid if it comes? Does it work? No, it doesn't work. What do I have to do to click on here, perhaps? And then we try. Oh, now it worked. So what is fully clear is that in the distribution grid, so on low voltage, which is the fast in kilometers, the greatest grid by length, we have more and more heat pumps in Germany, more and more PV, and more e-mobility, which is charge at home. In Baden-Württemberg, the state of Germany I live in, we have a so-called Solardachpflicht. That is, every new rooftop or every refurbished rooftop has to have at least 60% of photovoltaics. And this leads to the case that the utilities, the distribution, the DSOs start to stop people from connecting to the grid because the grid might be overloaded. Here on the right-hand side, you see a simulation, an electrotechnical, is a very sound simulation of what happens if that street would all have PV on rooftop, a car, a heat pump, and so on. The red color here indicates that the lines are heavily overloaded in that case, at noontime. It is not the transformer which is the restriction. It is the lines in the street. They will simply melt away. And you don't only have that problem at noon, you also have it in the middle of the night when heat pumps and EV is activated. So the lines can't carry the future. Which leads immediately to the fact, if you want to do it, because you cannot do with that kilometrage a line reinforcement all over, you need to have small batteries within the house or to curtail. But if you curtail, then the whole energy balance will not come into the future we want to. So at the end, we all will have a question of managing as well power limits, the lines, and energy limits, the batteries, within houses together at the same time. And we believe that one of the possible futures to solve that problem might be an energy packet grid. What is an energy packet grid? It has a backbone, it has routers, like an internet, where power is routed. And in every house, you have a so-called EP device. An energy packet is defined as a pre-negotiated quantized power flow between 2 EP devices, I'll define in a second, and they exchange a certain amount of energy. That can be done in several forms. I'll show that on the next slide. An EP device is a power converter, so power electronics, combined with a battery storage system, which has to be sized. We heard just in the last session talks about sizing batteries, and the controller communication equipment. That is already proposed and developed, also in hardware. So back to what is an energy packet, which then can be exchanged between these houses. So in the right moment stored, in the right moment sent and routed. Energy packet is defined by some shape, has 3 phases: ramp up, constant, ramp down, but the ramp could also be different. The energy packet could be defined in power mode. So you send a power packet. It could be in current mode, so electrical current has that shape and not power, or in a mixed version. That has different electrotechnical backgrounds. But please keep these 2 different forms with different shapes for the following in mind. Why do we need a line manager for one of these? You saw a congested line in red, because we have to avoid EP transfers which do harm to the grid, either because capacity exceeded, then the line would melt away, or the voltage would heavily exceed it, and then certainly you run into other problems like installation and so on. So we introduce a line manager software component involved in the negotiation phase of every EP transfer. You pre-negotiate and then activate the power electronics. The basic task for this is to evaluate the grid state resulting from a requested EP transfer, and then accept or deny a requested EP transfer by the routers. You have two subtasks: grid state calculation, that everything stays in bounds, and what are the relevant time points for the transfer and for the calculation. And you will see in the next slides that the shape of the energy packet makes a difference. So if you have here depicted are two requests, so in red, one in the positive direction and blue in the other direction, and the sum of these two is that what you see on the grid state. Yeah, here we used this other way of defining energy packets, and the sum gives a non-monotonic grid state transition. So if you have monotonic grid state transitions, then it suffices to calculate the states at these time instances. If you choose an energy packet of these forms, then you have to calculate every time point, as you can see here, because you don't want to exceed a certain limit. Okay. So without loss of generality, we deal with DC grids in the scope of it, but that can be transferred to AC grids. And the requirements are grid state has to be calculated based on currents and power set points in these different transfer modes. And the grid state calculation should be fast, yeah, because you want to have many transfers, and so as that you have a time boundary. What would be nice to have, but not necessarily, is to allow different transfer modes, so current or power modes, on the same EP device level at the same time. Yeah. Now we looked into solvers. Yeah, you can do a nodal analysis, simply Kirchhoff's rules, algebraic calculation. You can do it by Newton-Raphson. You could do it by fast linear power flow, which is a method in the literature, and that's what we propose, which is new. We call current operating point method, which allows calculation of voltage in the operating point and linearized current. So for the three modes I introduced before, in the current mode, the power mode, and the mixed mode, if you wish to do them together, you could either do Newton-Raphson, yeah, or the COP method. The nice to have version, having different transfer modes on the single EP device level, can be dealt with in what we propose as the new method. So how did we evaluate this new method? We used SimBench models as grid topology, 60 nodes. The test sequence was to set 40 trapezoidal EPs in power mode from the line manager requested, one after each other. And the evaluation criteria is we used the accuracy compared with ngSpice. ngSpice is an open source electrotechnical software for calculating grids. And the computation time. So what is the time? It's the time spent between request till decision. We firstly activated line manager in simulation mode, also for the trapezoidal version, so as we calculate every time instant in order to have more grid state calculation for a clearer comparison out of for accuracy and computation time. And the result you see here, ngSpice is the reference. This is the L2 norm of the voltage difference with respect to that reference. And in green, you see the fast linear power flow. In orange, our new COP method, in Newton-Raphson in blue, which is hidden behind the orange one, because Newton-Raphson and COP have tunable accuracy because they're iterative models. They can provide evidently more accurate results than the FLPF method, which is not iterative. So you have worse results there. With respect to computation time in the simulation mode, the lowest computation time, because it's not iterative, has FLPF here depicted in green. Our new version COP is close in orange to FLPF, and ngSpice and Newton are slower. Please look here at the magnitude differences in computation time on the y-axis. Now, if we say, since we use trapezoidal energy packets, we can also reduce the computation time by only looking at the end of the transfers. You remember what I said? Thereby, you can reduce the calculation time by one magnitude. Again, you see that the fastest one is FLPF and COP, and then you have in red ngSpice and in blue the Newton platform. So by that, we propose to you a new method called COP. It has not the lowest computation time because this is the FLPF method, but we're very close to the lowest computation time, but we are more accurate. The new method allows different transfer modes on a single EP device level concurrently. And we think that this new method is promising for future use in an energy packet grid. So this is what I had to propose to you. And thank you for listening. And I take heartily your questions. Thank you.